Hello, and thank you for joining us for another edition of our USGS Public Lecture Series. My name is Amelia, and I'm going to be your host and moderator today. As usual, we have some quick announcements before I introduce our speaker and to give you all a chance to get settled before we start. Next month, on July 28th at 6 p.m. Pacific Time, we will have USGS research geographer Prasad Tenkabale speaking about mapping the world from satellites, helping us understand global food and water security for the 21st century. I hope you can join us during the summer to hear his talk and others that we have lined up for you as well. Now, for those of you who are joining us for the very first time and you're watching this through your desktop and need to find the closed captions for this talk, you can click on the closed captions icon with the two letter C's, which are located at the bottom right-hand corner of your screen. And lastly, toward the end of the talk, we will open it up to the Q&A session. To submit your question, click on the question mark icon located on the upper right-hand corner of your screen. And now it's time to introduce to you our speaker. Joining us is Dr. Michelle Coombs. Dr. Coombs grew up in a small town in Maine, went to college in Massachusetts at Williams College, and moved to Alaska in 1995 to attend graduate school at the University of Alaska Fairbanks. She has lived in Alaska ever since, except for a 3-year postdoc at the USGS campus in Menlo Park, California. She started out as a geologist with the Alaska Volcano Observatory in 2004 and became scientist in charge at AVO in 2016. She lives in Anchorage with her husband, son, daughter, 2 cats, and 1 dog. Without further ado, I'm going to pass it over to Michelle, who will be talking about keeping tabs on the volcanoes of the last frontier, an update from the Alaska Volcano Observatory. Michelle, thank you so much for being here, and I will now hand it over to you.
Thanks, Amelia. Okay, can everyone see my slides okay?
Looks good.
Okay, thank you so much. Well, it's really exciting to be here, and thanks for inviting me to be part of the USGS Public Lecture Series. So today I'm going to talk about what we do at the Alaska Volcano Observatory, or AVO. So before I dig in, I just wanted to let folks know a little bit of background about AVO. AVO was created in 1988, and it's a cooperative or joint program between the USGS, who I work for, the University of Alaska Fairbanks Geophysical Institute. As Amelia mentioned, I was a graduate student up at UAF and worked with AVO as a grad student, and also the State of Alaska Department of Geological and Geophysical Surveys. And so we all work together as a team, and we have 3 overarching objectives with the work that we do at AVO. We monitor and conduct scientific investigations about Alaskan volcanoes. We assess their hazards associated with anticipated eruptions. And then finally, we provide timely and accurate information on volcanic hazards and impending dangerous activity to local, state, and federal officials and the public. And so in tonight's talk, I really want to talk about these 3 different overarching objectives that we have. I want to share some facts about Alaska's many volcanoes, and then I'll give a couple of examples of recent volcanic activity that we've responded to at AVO that kind of weave together these different themes. So before I get into the earth science, which of course is mostly what I'll be talking about, geoscience, I wanted to just start with some fun facts and figures about Alaska itself. Probably some or many of you joining the lecture tonight are from Alaska, but maybe some of you are less familiar. Probably everyone is aware it's a big state. It's the first or the largest state in the United States. It's got a pretty small population, however. It's 48th in population, and that leads to a really low population density. We're last in that. Each person in Alaska has a lot of room to roam, with about 1.25 people per square mile if you spread them out all over the state. And then one thing that'll we'll touch on again later in the talk that's pretty important is for how big a state we are. We don't have many roads. We only have about 36,000 miles of roads in the state. And so many of our communities are off the road system, and all of our volcanoes are off the road system. So that has some implications for how people get around and some of the hazards posed by volcanoes, and also add challenges to how we do our work as far as monitoring volcanoes. Okay, so I shared some superlatives in the last slide about Alaska. Well, Alaska has a lot of geologic superlatives too. In addition to volcanoes, which is mostly what I'll be talking about tonight, Alaska is the most seismically active state in the United States. It's home to more earthquakes than all other 49 states combined. It's also home to the second largest ever recorded earthquake on Earth that occurred in March of 1964, and it was the Prince William Sound, Alaska quake of 64. It was a magnitude 9.2, and you can see the slip area from that earthquake here, that area that I'm outlining right there. So Alaska has a lot of earthquakes, and most of them are related to its tectonic setting in the Ring of Fire. So probably most of you are familiar with this term, the Ring of Fire, which is a description of the tectonic setting of the Pacific Basin. So outlining the Pacific Ocean is a whole series of subduction zones that are very seismically active and volcanically active. And so as new oceanic crust is formed through the mid-ocean ridge spreading center, down the center of the Pacific, older oceanic crust is subducted along the margins of the Pacific Ocean underneath mostly continental crust. And that process of subduction of oceanic crust causes earthquakes at that interface right there. It also causes subduction zone volcanoes. So when that oceanic crust is subducted into the Earth's mantle, it releases fluids that are then, they interact with the mantle wedge that overlies the subducting slab, and they act like antifreeze and cause portions of that overriding mantle to melt and form magma. That magma then rises through the crust because it's more buoyant than its surroundings. And if enough magma accumulates and enough pressure builds up, that magma will continue to ascend and erupt onto the Earth's surface and form volcanoes. And it's that process of magma generation and ascent and eruption that forms all of the chains of subduction zone volcanoes that we see around the Pacific Ring of Fire, and is the cause for most of the volcanoes that we have in the state of Alaska. So here's a map zooming in on Alaska itself. And you can see, as I just said, most of the volcanoes are along that plate margin between the subducting Pacific Oceanic plate to the south and the North American plate to the north. We do have a few other volcanoes that are scattered in the interior or further away from the subduction zone, I should say. These are mostly basaltic volcanoes that are caused by some back arc processes or tectonic faulting and magma slipping up through there, but they're smaller and much less numerous than the volcanoes that we have along the arc. I also do want to mention over here in Southeast Alaska, we have a few volcanoes, and I'll talk about one of them at the end of the talk, Mount Edgecombe, right here. These volcanoes are not along a subduction zone, but are along a transform fault, where here the oceanic crust is sliding alongside the continental crust of the North American plate. And it's thought to be a leaky transform with a little bit of magma slipping up along that particular fault. The other thing I'll point out before I move on from this slide is that you can see two different colored symbols here. So historical eruptions from Alaskan volcanoes are shown in red. Those are eruptions that have occurred in the since the mid to late 1700s, when written records began in this area. And then in yellow, you see volcanoes that have experienced Holocene eruptions. And Holocene is a period of geologic time that has occurred since the last major ice age, so about the last 12,000 years. So those of you in Alaska may be aware of this, you may not, and others probably aren't aware, but we have a lot of potentially active volcanoes. We also have 3 volcanoes erupting right now. These are pretty low-level eruptions. They're not causing a lot of impacts to humans or infrastructure or anything like that, but we are keeping our eyes on them in case they become more significant. The most western of these over here is Semisopochnoi volcano. Semisopochnoi is an island in the far western Aleutian Island chain. And it's been having a pretty low-level eruption now for over a year. The photo that you see is actually from our web camera that we have out on the island along with our monitoring network. And data from that webcam are telemetered back to us and onto the web. And so we can actually keep tabs, if you will, on what's going on out there, despite it being several thousand kilometers away from our offices. Here in the middle is Great Sitkin volcano. It's about 30 miles from the community of Adak, also in the Aleutian Islands. It's been forming a lava flow since last summer, and you can see the nice lobes of those flows coming down from the summit crater up there. This is a photo taken on one of the very rare nice days out in that part of Alaska by one of the local Adak residents. And then finally, also erupting right now is Pavlov Volcano. It is one of the most active volcanoes in the Aleutians. It's erupted many times over the last few decades. The current eruption is pretty modest, pretty low level. Previous Pavlov eruptions have put ash clouds up to tens of thousands of feet. This eruption is mostly low level ash, and it's also forming some small lava flows. And it's about 36 miles away from the nearest community of Cold Bay, which is where this picture was taken from. So here's another map showing Alaska, and the red symbols on this map are showing volcanoes that have erupted in the last almost 35 years since 1988, when AVO came into creation. And so it shows we've had 20 volcanoes erupt over 65 times in those 3 decades. So just reiterating, it's a volcanically busy place. And you can see some of the photos down along the bottom there are some of the more notable eruptions. Cleveland has erupted many times, 16 times. Okmok only a couple, but with a pretty significant eruption in 2008. Bogoslav volcano, which I'll talk about later in the talk, and then another frequently active volcano, Veniaminov. So I wanted to share this figure here because it shows a way that volcanologists or volcano scientists use to kind of measure the size or the magnitude of volcanic eruptions. It's called the Volcano Explosivity Index, or VEI. And most of the volcanoes, or most of the eruptions that I've just walked through, are really on the small end of this index. So in the last 30 or 35 years, I believe in Alaska, we've had a single VEI4 eruption. That was Kasatochi Volcano in 2008. We've had a handful of BEI3 eruptions. Those include the 2 eruptions of Mount Redoubt in the Cook Inlet area, and then lots and lots of BEI 0, 1, and 2 eruptions. This figure, which is created by other USGS scientists, mostly highlights other eruptions outside of Alaska that you may be familiar with. Pinatubo, 1991, Mount St. Helens, of course, was somewhere between a VEI 4 or 5. And then, of course, our super eruptions from Yellowstone, which are incredibly rare, but incredibly voluminous, would be down here at the bottom. So most of our recent eruptions have been pretty modest in size with regional or localized impacts. That doesn't mean, however, that Alaska is not capable of having larger eruptions, including some in historic time. So this slide describes what was the biggest eruption of the last century and also the largest historical eruption in North America. That was an eruption that occurred over 100 years ago in 1912. It was from a volcano called Novarupta Volcano on the Alaska Peninsula in what is now Katmai National Park and Preserve. And over a period of about 3 days, this volcano produced over 3 cubic miles of ash and pumice. And you can see the extent of the ash that came out of this particular eruption shown here on the map figure. And then some of these other notable but much smaller eruptions that are historic are also shown. And Novarupta 1912 really dwarfs them. And then similarly in the upper right, you see here's Novarupta, 3 cubic miles of material erupted, and some of our other Alaska volcanoes down here for reference, and then Mount St. Helens, which everyone thinks it was a very substantial eruption, but the amount of material erupted was much, much smaller than in Novarupta. Back in 1912, Alaska was sparsely populated, and miraculously, no one was killed during this eruption, despite the huge volumes of magma that was erupted. This picture here shows what the area looks like today. The area that was covered locally by ash from the eruption is called the Valley of 10,000 Smokes. It's a spectacular destination in Katmai National Park if you ever have a chance to visit. Okay, so some eruptions in Alaska are really large, some are not so large, but one thing that almost all Alaskan volcanoes have in common is that they're really remote. In other volcanically active parts of the world, some active volcanoes have pretty dense populations right up on their flanks. This is a photo on the right of Unzen Volcano in Japan. It had a series of eruptions in the 1990s, and you can see a lot of folks living right up on the flanks of that volcano. In contrast, on the left is a photo of Shishaldin Volcano on Unimak Island in Alaska. Shishaldin is the volcano in the foreground with a couple of other older volcanoes in the back. Most of our volcanoes are pretty far from communities and far from infrastructure. That doesn't mean, however, that they don't pose hazards to Alaska residents and visitors. The volcanoes pose a whole array of volcanic hazards. You can see them depicted in this diagram. Most of those hazards are really going to affect folks, like I said before, that live on the flanks of the volcanoes or live near valleys downstream from where the volcanoes might drain. So things that might affect people locally are lava flows, pyroclastic flows, lahars or volcanic mud flows, landslides. Those are all proximal hazards. Most of our volcanoes in Alaska are far enough that these proximal hazards are not going to impact our local communities. However, many of our volcanoes erupt explosively, and when they do that, they produce ash clouds. And I'll talk about the impacts of volcanic ash over the next couple of slides. So what is volcanic ash? Well, very simply, it's really a grain size designation. It's how big the particles are of volcanic material that are erupted out of the volcano explosively. So volcanic ash is small. It's less than a couple of millimeters across, and it's made up of sharp fragments of rock, volcanic glass, and minerals. And you can see in this upper photo is a scanning electron micrograph of what these ash particles look like. It's produced during explosive eruptions, and it's carried downwind where it falls to the ground. So ash can be hazardous both when it's in its airborne state, and I'll talk about that, and then also when it falls to the ground. So some of its properties are shown here. It's very heavy. It's pulverized rock. So unlike fireplace ash, which is maybe what some of us visualize when we think of ash, fireplace ash is light. Volcanic ash is heavy. If it falls in substantial volumes, it can collapse structures and cause other damage to structures. It's easily remobilized. If it falls to the ground and if the conditions are dry and windy, that ash can get kicked up again and hazards can be ongoing, not just after the eruption. In fact, just today, here in Alaska, down by some of our volcanoes, including Aniakchak and Novarupta, we're having windy conditions and we're getting pilot reports of remobilized ash just today. So it could be an ongoing hazard. It's an air quality contaminant. It's unhealthy for humans to breathe when it's very fine grained. It could be chemically corrosive, and it can also block sunlight. During eruptions, day becomes night, as is described in many reports of long eruptions. And ash is a particular hazard to aviation. So I mentioned near the beginning of the talk that Alaska doesn't have a lot of roads. We're very reliant on aviation for travel, for movement of goods and cargo, all kinds of things. And when a plane encounters an ash cloud, that can cause a lot of damage to an aircraft. The primary hazard that has been recorded over the decades is that when volcanic ash, which is made up of silicate particles, is ingested into a very hot turbine engine of a jet aircraft, it can actually melt and then precipitate on other parts of the engine, causing that engine to seize. Even for non-jet aircraft, it can cause damage to all kinds of other parts of the aircraft. It's very abrasive. It can sandblast windows and other parts of the aircraft body. It can wreak havoc with electrical systems, etc. This was brought home very gravely in Alaska in 1989 during an eruption of Mount Redoubt volcano, which is here in the Cook Inlet area across Cook Inlet from Anchorage. Jet was coming from Europe and knew that there had been generally eruptions of the volcano, but the volcano erupted again, and the pilots were unaware of the position of the ash cloud, and that jet encountered the ash cloud, lost power to all 4 of its engines, dropped about 13,000 feet, and was able to finally, once it was out of the ash cloud, turned off or shut down, powered down its engines. That allowed the engines to cool. The volcanic ash was able to get off of the engines. The engines were miraculously restarted by the pilots, and the aircraft was able to safely land with everyone on board. I believe there were over 200 people on board that aircraft. It was a miracle they were able to land. It was very fortunate. All of the engines, it was a very new aircraft. All of the engines had to be replaced, and it suffered about $150 million of damage in today's dollars. So definitely a wake-up call. There have been just a handful of global incidents like the one I just described, but definitely serious. Even in cases where we have eruptions where there are no aircraft encounters with airborne ash, because of the potential hazard, eruptions can have huge impacts just on disruptions of air travel. In 2010, there was a prolonged eruption in Iceland, shown here, and really wreaked havoc on European air travel for several weeks. So just a few facts and figures about Alaska and aviation. The state really does have kind of a special relationship with its aviation sector. The Anchorage Airport, the Ted Stevens Airport here in Anchorage, it's a very busy cargo airport, second largest airport in the US for cargo and fifth largest in the world. Lots of passengers coming in and out of Anchorage as well. In general, the airspace over Alaska's volcano is very busy. The so-called NOPAC, North Pacific air routes, fixed air routes, go right over the volcanoes because that's the Great Circle route between North America and Asia. And a few years ago, in trying to understand potential hazards related to our volcanoes and overflying aircraft, an analysis showed that in 2016, over 60,000 passengers per day traveled over Alaska's volcanoes. And then finally, I mentioned this earlier, but aircraft are among the main modes of transportation in the state. So even if you're not dealing with these trans-Pacific larger aircraft on longer routes, just the smaller regional aircraft are hugely important to our communities. 82% of Alaskan communities aren't connected to roads. So how do people travel? How do goods get in and out? By air. And so if there's a volcano nearby that's erupting, that has a serious impact. Okay, so now I want to talk a little bit. We've talked about how many volcanoes we have, the fact that they erupt a lot, the fact that when they do erupt explosively, this can pose hazards. How do we kind of assess and quantify the relative hazards posed by our different volcanoes, and how do we try to understand how to best monitor those volcanoes moving forward? So the key to understanding what any one volcano is capable of is by looking at its past history, what it's done in the past. And so we use a host of methods to try to understand or assess a volcano's hazards. So we use historical records. You can see in the center here a timeline of events from one of our volcanoes, Boguslav. We pieced together these historical records to try to understand what past eruptions look like. We do numerous geologic studies where we look at the stratigraphy and structure of volcanoes and date the deposits to try to get eruptive histories that go back further in time than the historical record. And we've also really started to try to use indigenous knowledge to understand past events at volcanoes. And we put all of these together to try to say, what has a volcano done in the past, and what is it capable of then in the future? So the approach that I just talked about is understanding these volcanic hazards. And so these are dangerous natural phenomena produced by a volcano. But then we also want to look at exposure. How are people and property vulnerable to volcanic phenomena? And then we can combine these two together and get what we call a volcanic threat. Back in 2018, we did John Ewart et al. Did a threat assessment of all of the volcanoes in the United States. This isn't just an academic exercise. This really helps us focus our monitoring and our scientific studies and see where more work is needed and where the most monitoring is needed. I know this figure is a little bit hard to see because it really covers a big geographic area. But before I zoom in on Alaska, I'll just point out that each of the volcanoes here in the US are color-coded by their threat level as determined during this assessment. And so very high volcanoes are in red, high is orange, moderate yellow, etc. And I will point out, if you look here in the Pacific Northwest, in the Cascades, there are many very high threat volcanoes. Those volcanoes in the Cascades don't erupt a lot, but they have a lot of people who live very close to those volcanoes. So that's how you end up with a high number of very high threat volcanoes there. But let's zoom into Alaska. So in Alaska, according to this most latest assessment, we have 5 volcanoes that fall in the very high threat category, or the highest level there is. And I've shown photos of them here and shown where they're located in the state. So 2 of them are out in the Aleutian Island chain. These are Makushin Volcano and Akutan Volcano. These volcanoes are a little bit different than many of our other volcanoes out in the Aleutians, in that they're located on islands with communities. So Makushin is on Unalaska Island next to the community of Unalaska Dutch Harbor, and Akutan is on Akutan Island, located near the village of Akutan. These volcanoes also erupt very frequently. So the combination of local folks having exposure to the hazards, and then the frequent eruption puts them in the high risk category. The other 3 are volcanoes that erupt pretty frequently. They're located in what we call the Cook Inlet region of Alaska, or South Central Alaska, right up here. So Anchorage is a little hard to see, but right where my red dot is approximately. And so all of these volcanoes have erupted multiple times in the last few decades, and they erupt very explosively, and they cause major disruption to aviation. They've all caused ashfall on South Central communities on the Kenai Peninsula, and Spur and Redoubt have put ash on Anchorage as well. And then Redoubt, in addition, in its last 2 eruptions in 1989 and 2009, had lahars fill this valley here, the Drift River Valley, and come very close to and partially inundate an oil terminal. The train's going by, sorry about that. Partially inundate an oil terminal out at the mouth of the Drift River. So that's another added element that added to Redoubt's threat score for sure. Other volcanoes, though, we have lots of volcanoes. 30 are high threat, and then about 50 are at these lower threat levels. A lot of these little orange volcanoes are out here on uninhabited islands, but again, they have a high possible threat to aviation because they are really frequent eruptors. Okay, so I want to kind of pivot a little bit and talk about what do we do to address all of these hazards and all of these volcanoes. So there is some good news, and one of the things that makes studying volcanoes to me so fascinating and rewarding is that they provide warning before they erupt. So this figure on the left shows a whole list of different types of natural hazards. And then it's just schematic, but it shows, precursors or a period of warning before an event happens, and then the event itself. And so earthquakes, as we know, they don't provide any precursors, no warnings to an earthquake, and that can have devastating consequences. Other natural hazards might provide days or hours of warning, for example, in the case of a hurricane. Volcanoes provide sometimes days, weeks to months, or sometimes even years of unrest or precursors before they erupt. The reason for this is because, as we talked about before, volcanoes erupt because new magma is ascending into shallower levels of the crust and occasionally makes it to the surface in eruption. And as that magma rises, it causes a variety of phenomena. It causes the rock around it to fracture, which causes earthquakes. It actually changes the shape of the volcano. It causes ground deformation. It gives off gases as it rises, and those can be measured by different techniques. These are just a few of the examples of types of unrest that we can measure to try to forecast an impending eruption. So how do we monitor volcanic activity, or volcanic unrest, I should say? Well, we do it any way we possibly can. We monitor some of the signals I just described in the past slide, as well as a few others. So I have a few slides that we'll just walk through here. So I would say the types of techniques that we use fall into two broad bins. One are ground-based sensors, and the other bin would be remote sensing techniques. And really the bread and butter of our monitoring program at AVO and other US and other volcano observatories is our network of ground-based sensors. We like to put these sensors as close to the volcano or on the volcano as we possibly can. You can see in this map here showing the southwest part of Alaska. And, this is the familiar chain here. And what all of these insets show, and they're all at the same scale, they show all of our sensors in our different subnetworks as part of our overall monitoring network. And so the gold standard for a monitoring network on a volcano is to have sensors all around surrounding the volcano, and as I said, at least some up close if you can. And we also use a variety of different instruments. I would say for when this work first started, most stations were simply seismic stations, so a buried seismometer in the ground to look for earth motions. Over the years, we've really expanded our repertoire to include these other types of sensors, and I'll talk about each of those in turn. The other thing I just wanted to mention with this slide is you can see on the right a couple of photos of examples of what some of these stations look like out on the landscape. None of our sensors are accessible by road. They all require visits by helicopter, sometimes by boat, and then taking a boat with a helicopter, and then taking the helicopter to the island. So, excuse me, maintaining this network of over 200 stations excuse me, is challenging. Summers here in Alaska are pretty short, and so the short summer field season is pretty busy, and we're right in the middle of it right now. So I mentioned a second ago that one of the main tools that's been used probably the longest is using seismic signals that are produced by volcanoes to try to understand what that volcano is doing. Volcanoes produce a whole variety of seismic signals. When that magma is moving towards the surface, it causes rock-breaking earthquakes. Once the volcano has erupted, or when it's in eruption, you can actually detect the explosion seismically. You can also see seismic signals that reflect types of phenomena that occur during the eruption, like pyroclastic flows or lahars or rock falls. All of these produce unique types of seismic signals. One challenge, though, is trying to distinguish the volcanic signals from the non-volcanic signals. I mentioned earlier, Alaska has a lot of tectonic earthquakes, and those often happen nearby the volcanoes. And so we really, sometimes it can be challenging to tease out the difference between a tectonic fault or a tectonic earthquake and a volcanic earthquake. Other things can produce seismic signals, moving animals, or even a helicopter landing. A technique that's newer but is becoming really useful for us in Alaska is using infrasound. So the map on the upper right shows in red all of the infrasound sensors that are in the AVO network. And infrasound sensors detect acoustic or sound waves, but ones that are very low frequency, so below about 20 hertz, which is the threshold of human hearing. So it's sound that we can't hear with our human ears, but all kinds of explosions or atmospheric disturbances will make infrasound signals. It's been used, for other applications to look for other types of man-made explosions, but we found that it's very useful for detecting volcanic explosions. Because we have so many volcanoes in Alaska and not all of them have ground-based monitoring, sometimes we aren't able to forecast an eruption, but we can use infrasound to detect eruptions. And the other powerful thing about infrasound is that these waves will travel from where they're created at the site of an explosion for hundreds of kilometers. And so you don't have to have as many infrasound sensors along the whole arc to be able to detect eruptions. So we use a combination of both local infrasound sensors, but also a backbone of regional arrays that provide some level of detection so that volcanoes don't catch us by surprise. The third major type of ground-based sensor that we use are sensors that look for ground deformation or just movement of the ground as volcanoes either swell because of new magma or sometimes they subside. The photo on the left is a installation of a GPS antenna right here. And then this particular site also has a tilt meter buried that can look for very subtle variations as it tilts in one direction or another. In Alaska, we don't have deformation instruments on as many of our volcanoes. We have them on just a few. But where we do have a GPS network, it can be very powerful for looking, as I said, at ground inflation or swelling of the volcanic edifice. The figure that you see on the right is an example of that. This is Akutan Island, and it's showing different periods of inflation shown by upward movement shown by the green arrows, and then outward movement shown by the blue arrows. So I mentioned that we don't just use ground-based techniques, again, because we don't have ground-based sensors on all of our volcanoes. So we're pretty reliant as well on remote techniques. And one that we've used for many years is satellite remote sensing. So we use this in a variety of ways, and as new satellites come on board and new sensors become operational, the whole host of satellite data that we're obtaining is really grown over the last few years. But one thing that we've done for a long time is use weather satellites to look for airborne volcanic ash. And these satellites provide data multiple times per day, and that's what you see here on the left. This in blue, this big blue streak is an ash cloud that was produced during the 2016 eruption of Pavlov Volcano. So that's a type of analysis that we do. We're always looking at satellite data for that type of signal for airborne ash. Less frequently, but to kind of fill a different niche, we don't get these types of images as frequently. But synthetic aperture radar images taken by satellite can track the growth of lava domes or lava flows during effusive or lava forming eruptions. They can also show changes in the surface, like sometimes volcanoes have ground cracks or pits that form. And so that type of radar data is very good at looking at surface change. And then finally, we can use satellite data to look for thermal changes at a volcano. So on the right is a recent image of Pavlov Volcano, and I mentioned before it's having a low-level eruption right now. And that little orange area in the center is some active lava that's showing up as hot in this shortwave infrared image. We also use satellite data to look at gases that come out of volcanoes, predominantly sulfur dioxide or SO2. So gas is a really great indicator of magma on the move, and we use satellites, as you can see on the left. Here's a really impressive satellite image of the SO2 cloud from Kasatochi in 2008, and you can see it, sort of swirled over much of North America. We also do more targeted surveys, and that's what's shown on the right. That's the track of a helicopter with a gas sensor attached to it, looking for the gas plume being emitted by Cleveland Volcano. So you can see in this area here, where the gas concentrations were elevated, it kind of maps out where that gas plume was moving. And then importantly, something just very fundamental, but very important, are just visual observations of the volcanoes. As I've mentioned, Alaskan volcanoes are remote. Often the weather's bad, but when the weather's good, just getting eyeballs on what the volcano is doing is extremely useful. We have a number of web cameras that are part of our monitoring networks, and you can see examples along the top there. You can always go to our website and see live web camera images, most of them updated about one every hour. We also really rely on mariners and pilots and local residents to make observations, to take photos and send them in to us. And that's what's shown along the bottom, a couple of examples from Makushin and also Boguslav. And then finally, as far as monitoring during eruptions, one thing that's really wonderful to be able to do, but is often a little bit more challenging, is collecting samples of the material that is erupted, either ash or rock, lava, pumice. That allows us to, if we can get a time series of those samples, it allows us to understand where that magma is coming from in the crust, how it's changing through time, how that eruption might proceed into the future. Okay, so I'll go through my last few slides quickly so we have time for questions. I just wanted to give a couple of examples of some unrest and eruption that we've been dealing with over the last few years. And so this figure shows, it's just a very schematic figure, and it shows that volcanoes can erupt quickly, without much warning. And I'll show an example of that with Boguslav Volcano. It went pretty quickly with very little warning right up to eruption here. And then sometimes volcanoes will have a period of unrest, and that could be earthquakes or gas or deformation. And then they just kind of bubble along for a while, and they might erupt or they might go back to sleep. And we're dealing with that situation right now at Mount Edgecombe Volcano. So Boguslav erupted suddenly and without warning, starting in the winter of 2016. It's a small island volcano north of Dutch Harbor on Alaska in the Bering Sea. And it was just a tiny little island with most of the volcano being underwater. And so we didn't have any monitoring instruments on it. And we got a pilot report one day in December of 2016 saying he saw an ash cloud coming out of the ocean. And that is, in fact, this photo right here that he snapped. And one of our duty scientists took that call from air traffic control and listened to the report and said, I think that sounds like Boguslav. And indeed it was. And little did we know at that time that Boguslav would go on to erupt over 70 times in the next 9 months. It had 70 ash clouds, and some of them went up over 40,000 feet above sea level. So definitely in an area that would, altitude that would impact aviation. So what did we do to try to monitor and provide warnings about this activity on an unmonitored volcano? Well, clearly we had missed the precursory phase, if there even was one. And so we really focused in on this very short-term monitoring window. And we wanted to see, could we use our distant seismic stations and our infrasound instruments that were further away to try to detect any activity at that volcano? And if not, could we at least detect when an eruption happened and then characterize the resulting ash cloud? How high was the ash going? Where was the wind going to blow the ash? And so on the right here are examples of 3 of these different eruptions during this eruptive sequence. And so the black trace here is the seismic data, and then the gray trace is the infrasound data. And you can see in some of these eruptions, distant seismic stations picked up pretty strong earthquakes. And then right in this, right here, is where the explosion started. And then the explosion went on for a while and then ended. And then sometimes the explosion would just start without any precursory signal. So what I wanted to kind of draw your attention to was kind of how, like I said, how we respond to these sudden and hard to forecast eruptions. And so these blue bars that you see down here, those show some of the actions that we took during these events. So we'd get an alarm that would say, oh, infrasound and seismic is elevated. We would assess the data. And once it looked like an eruption was either happening or about to happen, the very first thing we would do would be to call the FAA and tell them, the volcano has erupted. Please tell anyone in the area to avoid that area. And the other thing that I want to draw your attention to are the orange and red bars. And those show when we change what we call our aviation color code. And I think the very next slide is going to, so here, this just shows all of the people that we work with and the people that when we have volcanic activity, we would call. In this particular case, our first call was to the FAA because of the aviation hazard. And I mentioned the color codes, so changing the volcano's color code to orange or to red. This is a shorthand system that we use to quickly communicate the status of the volcano. And in the case of these explosions, once we had confirmed that an ash cloud was present, we would raise the color code to red. And that quickly communicates to our partners and to the public the status of the volcano. And then finally, I just want to show a couple of more aspects of the Boguslav response. One of the things that we really wanted to help communicate to people was, is there going to be potential ashfall on communities? So anytime there was one of these 70 events, we would initiate an event-driven model run using our ash dispersion model, Ash 3D, and that would tell us where is the ash cloud going to go, how much ash is going to fall, and would it, how would it fall on communities? We can even say when the ash is expected to fall and the duration of the ash fall. And then on the right, this map shows Boguslav at the center there. And this shows all of these sort of pink colored polygons are individual volcanic ash advisories that were issued by the Anchorage Volcanic Ash Advisory Center, operated by the National Weather Service. And we would just work very closely with the Weather Service during that eruptive sequence to help them understand what our monitoring data were saying and coordinate them about what the ash cloud was doing. And then finally, for my last couple of minutes, I would just like to talk about Edgecombe Volcano. I mentioned this at the beginning, that it's in a part of the state that we don't usually pay attention to. But back in April of this year, one of my colleagues at AVO got a call from her relative who lives in Sitka saying, hey, Cheryl, we see this earthquake was located by the Alaska Earthquake Center right under Mount Edgecombe. Does this have to do with the volcano? And Cheryl said, I'm not sure. Let me ask the geophysicists at AVO. Well, she did, and they pulled up data from the nearest seismic station, SIT, which is located in Sitka, which is about 20 miles from the volcano. And sure enough, when they pulled up the data, this is what they saw, a swarm of small but plentiful earthquakes associated with this single located event. And that really got our attention. And we put out an information statement about this activity. And it certainly got people's attention in Sitka. So Sitka, which is very close to Mount Edgecombe, you can see in these lovely photos, here's Mount Edgecombe and here's the harbor of Sitka. About 8,500 people live there, and they were very curious about what their volcano was doing. They all thought their volcano was inactive or dormant, so we're really surprised at this activity. So we spent a few days, fielding media requests, talking to people, and also digging more into the data. And so we really wanted to figure out, okay, we don't have a monitoring network on this volcano, but what can existing data tell us? Well, we did two things that really suggested to us that this activity was related to the volcano. On the left, you can see a figure that shows a whole series of satellite aperture radar images analyzed together to make an INSAR figure. And so the colors that you see there are deformation in this circular pattern that's centered just to the east of Mount Edgecombe. So in the center of this red region, there was over 25 centimeters of uplift, concentrically centered east of Mount Edgecombe and concentric around that area. That deformation started back in 2018. So we were unaware of it, but it had been going on for a few years because this is not a volcano that we expected to be active and not a volcano that was part of our routine monitoring. That really got our attention. The other thing, we went back and looked at the seismicity in the area using the regional seismic network. And it's a little bit hard to see, but first you can see all of these earthquakes out here. This is the transform fault, the Queen Charlotte transform fault that I mentioned earlier. So there's a lot of seismicity along there. But then this whole cluster under Mount Edgecombe, which is on Crusoe Island. And we looked back, and that seismicity started in about 2020. So taken together, it seemed that we had deformation that started about 4 years ago, and then earthquake activity that started about 2 years ago. And the most plausible reason for this activity would be that there's a new intrusion of magma underneath the volcano. Well, when we put that information out, you can imagine that folks in the area were even more curious and desiring more information, I'll put it that way. And so our first step was we realized that this is a part of Alaska where people weren't used to volcanoes being active. And so there honestly was a fair bit of alarm, might be too strong a word, but concern. And so I went with my colleague Cheryl to Sitka. We did a number of community talks and radio interviews and outreach events and just tried to reassure people that sometimes volcanoes have magmatic intrusions and then they go back to sleep. And if Edgecombe is going to erupt, we expect a significant amount of more precursory activity in the form of shallower earthquakes, stronger earthquakes, et cetera, et cetera. The other thing that we did is we worked with the U.S. Forest Service, who manages the land that Mount Edgecombe is part of, and in the Tongass National Forest, and we were able to install a new site with a GPS and a seismometer, and that's been really useful to help us see smaller seismic events, smaller earthquakes that we would not have been able to see with the regional seismic network. So with that, I'm going to wrap up with those last two kind of examples, one very short-term type of forecasting and one that we're still in the middle of, longer-term forecasting. I want to encourage folks, if they want to learn more about AVO, our website is a great source of information about ongoing current activity, but also past activity, photos, publications, etc. You can also sign up to get notifications about activity in Alaska or in any US, for any US volcanoes using the USGS Volcano Notification Service. And you can also receive or find any of our formal notices on our social media accounts, but also a lot of other fun volcano information as well. So thank you very much for listening, and hopefully I left a little bit of time for questions.
You certainly did. That was fantastic, Michelle. I mean, my gosh, you covered so much history and facts, and it's amazing the work that you do out there. Thank you again. Before we begin with the Q&A portion of the lecture, a friendly reminder, if you would like to submit a question, click on the question mark icon. We've been monitoring questions so far that have come through, and I'm going to go ahead and ask those out loud first, and I'll do my best to get to every single one of those, okay? We have Anonymous who wants to know, with all the earthquake activity in Alaska, have you ever found that the activity can cause one of the many volcanoes to erupt?
That is a great question, and we get that question a lot. And the answer is, so just kind of zooming back, you know, they're both our tectonic earthquakes and our volcanoes are related generally to subduction, as I described. But the earthquakes that we see associated with the volcanoes are due to magma movement, and the earthquakes along tectonic faults are unrelated. So I just wanted to kind of set the stage with that. So generally, the subduction zone and regional faults are just different systems than the volcanoes themselves. However, looking at triggering of eruptions or triggering of even seismic activity of volcanoes after big tectonic quakes has been an area of, you know, people are really interested in that. I will say, just first principles, it's not something that, it's never been proven to happen, and it's certainly not something that we see with any regularity. In fact, in Alaska, I can't think of a single case of an eruption being caused, you know, by an earthquake. One thing that we sometimes do see is the seismic activity at volcanoes can increase a little bit after the big earthquakes. So it's definitely an area of active research, but it's not something, we don't usually see that one-to-one link.
Excellent. Thank you. So I was curious just myself, how often do scientists go out into the field to collect the eruption samples that you were talking about?
Yeah, great question. Not as often as we would like. It's, you know, this past year with all the kind of low-level eruptions I talked about, last year we were able to get some samples from Semi-Sopochnoi, Great Sitkin, and Veniaminoff, which had erupted the year before. So that was actually a very good record for us. We do have other eruptions, though, where it's just because of weather or, you know, remoteness. Some eruptions go unsampled. Our bigger eruptions in Cook Inlet, we do try to make a much bigger push to get out there and do the sampling. But it's expensive, it's challenging. Sometimes the weather doesn't cooperate.
Yeah, lots of different factors that can kind of keep you from grabbing all those samples.
Yeah,
that makes sense. Anonymous wants to know, are there any volcanoes near major population centers that are of concern?
Yeah, great question. Right now in Alaska are the ones closest to the major population centers are pretty quiet. So, you know, most of the population of Alaska lives in South Central, kind of the Anchorage, Matsu Valley area, and then down on the Kenai. And our Cook Inlet volcanoes are very quiet right now. So that's good news, I guess.
Right. Let's see here. Another Anonymous wants to know, do you ever give tours of the AVO office?
Well, we just today learned that we're back in the high community transmission rate for COVID, which is means that's going to have an impact on tours. I'll go back to pre-COVID. We do tours, especially for school groups, you know, university groups. We've done individual tours on occasion. We don't usually do sort of open public tours, but we have on just isolated examples or cases. So yeah, we love having people come in and see what we do, but we don't have like public scheduled tours, put it that way. But we try to get a lot of school groups through.
Oh, that's great. It's great with schools. Get that outreach out there with the kids.
Yep.
So one thing that I was wondering about, I noticed that you had a bunch of there was a slide that you showed with a bunch of television monitors, or it looks like television monitors, and probably it's a lot of the data, but I know it's hard to know when a volcano is going to start to erupt. Is there 24-hour monitoring of any of these volcanoes?
Really good question. Yeah, that's something, yeah, there's a lot to cover, so I didn't really get into the nitty-gritty. So what we do, we kind of, it's changed a lot over the years. So we rely a lot more on alarming and alerting. So we can have computer algorithms that will look at, say, the seismic data, and if one of the algorithms sees, elevated levels at a volcano, we'll get an alert on our cell phone, basically, in an email, and look at that. We do have folks look at data also just routinely, multiple times a day. If we have a significant eruption, say, Mount Redoubt were to start erupting again, we would go to 24/7 staffing in our operations center at the observatory, and that's both to look at the data, but also to field inquiries and work with our partners and all that. So we do staff up to 24/7 when we need to, but usually we're not a 24/7 operation, and we're relying more on alerting and duty personnel keeping their cell phones close. They get pinged in the middle of the night.
Right. That's awesome. Thank you.
Yep.
Anonymous wants to know, how closely do you work with volcano centers in other countries?
Oh, yeah, great question. So I didn't get into this a lot because I had a lot to talk about just with Alaska. But Alaska is one of 5 volcano observatories in the US. And then another part of our USGS volcano program is called the Volcano Disaster Assistance Program, or VDAP for short. And VDAP is partly funded by the USGS and partly by the USAID, so kind of the international aid part of the US government. And VDAP goes in and works with observatories and in other countries and helps them. Sometimes we provide instrumentation for them or expertise. We don't do the work for them, but we try to provide training and empowerment for them to improve their capabilities at other observatories. So that's one of the things that we do. And then just in general, volcanology is kind of it's not a huge giant discipline of science. And so we do try to we work with other countries as much as we can just to share what they're doing, and we tell them what we're doing and we hear what they're doing to just try to improve how we do our work at the observatory. So there is a lot of international collaboration in that sense as well. You're probably familiar with the recent eruption in Tonga that happened just a few months ago, and so we're working with Tongan geologists and people in New Zealand to try to help them improve their monitoring. So it is kind of an international affair in a lot of the ways.
Okay, awesome. Yeah, no, I've heard of VDAP before. They do a lot of great work.
Yeah.
So we have one more question here, and you've done so much, and you're scientists in charge of AVO and everything, and for all the women and young ladies that are wanting to pursue this field of volcanology, what inspired you as a woman in science to just go for this?
Yeah, wow. Well, thanks for asking that. I could never have imagined that I'd end up doing this exactly, for sure. It's been a long path, but as a student, in grade school and high school, I just loved science of all kind. That was always my favorite subject. All my favorite subjects were science. I went to college. I thought I was going to study astronomy, but it was not that interesting to me. And I took a geology class as a freshman, and it was fascinating. I got to be outdoors and learn about the natural world and do science, but yet kind of understand about the natural world around me, and that was very appealing. So I would say I got hooked into geology in college, and just kept kept trucking ever since. And I feel very fortunate now to work at AVO because it's a great place to combine science and scientific research, but also apply it, right? So I feel very fortunate. It's a great place to be. But yeah, I would say, starting out, just follow your interests and work hard, and you never know where you'll end up.
That's right. Well, the USGS is very lucky to have you, and thank you so much, Michelle, for your talk today and for answering all those questions from our audience.
You're welcome.
So thank you.
You and Mitch for making this really fun and easy. No one else.
You're very welcome.
But he's behind the scenes running everything.
That's right. That's right. Well, it was our pleasure.
Okay.
And hopefully we'll have you back one day in the future.
Sounds great.
Well, thank you again, Michelle, for your wonderful lecture, and thanks to all of you for joining us this evening. Michelle's lecture will be available for on-demand viewing in about a week on our website at www.usgs.gov/PLS. You can also see many of our previous recordings of our lectures on the website under the multimedia section for videos, so check those out. If you would like to subscribe to be part of our mailing list, feel free to send us an email at wmcesic@usgs.gov, and we will happily add you to the list. So for next month, please join us again, July 28th at 6 p.m. Pacific time for Prasad Tankobel's talk on mapping the world from satellites, helping us understand global food and water security for the 21st century. We will see you next time. Goodbye.